starting at a state 1, you're ending at a state 2. Or you're starting at an inlet, you're ending in the exit. But you wrote state 1, state 2, and at state 2 you said was this temperature and pressure, and then the inlet, which you called state 1, was this temperature and pressure. So what that's telling me is that this is on the left-hand side, and then this is on the right-hand side. But based off of the word problem, it seemed like you were trying to assign this temperature and pressure to the whole thing, so technically this would be the outlet, and then this would be applied to the whole thing. Does that make sense, what I'm saying?
I'm sorry, I'm not following super well.
So, the way that the problem is written, it is not correct in that you can have a temperature and pressure for this whole thing.
Yeah.
You can for a reaction vessel, because maybe your reaction vessel is undergoing chemical reaction at a certain temperature and pressure, and that's okay. But for this injector, I wasn't sure what the function of this was. Based off of it seemed like you were trying to say that temperature and pressure was increased, which is what you did in this solving for work.
Yeah, because like the whole idea is that the fluid goes from the injector to the reactor and just increases in temperature.
Yeah, but
due to
what the injector does, like has flow going through it, so it's going to manipulate the fluid for some purpose. If not, then we wouldn't need an injector. We would just go from this furnace to the preheater and put those two into the reaction vessel.
Yeah.
But the function of this injector seems like you're trying to like increase pressure, but here you're saying it increases pressure and it increases temperature. But if it's an incompressible substance, it's only going to do one of those.
Okay.
So if you wanted to, you could say that it's coming in at a certain temperature, and it is isothermally, so at a constant temperature, increasing pressure. So this would be, this injector's acting as a pump in that case.
Okay.
Does that make sense?
A bit more. I mean, I had to pass over what you said like a few times.
Okay. So you're going to need a different pressure down here. You can keep this at 2 megapascals if you want. Or if you keep this at 2 megapascals, you need to increase this to like, okay, yeah, maybe this would be the 2 megapascals and this would be the 20 megapascals, but the temperatures would be the same.
Are you talking about the temperature in like the little tube that feeds the contents of the injector into the reaction vessel? Because you're saying this, and I'm noticing that you're pointing at like the beginning of the injector, and then like at the point where the sludge flows into the reaction vessel.
Yeah. So this has a temperature and pressure. This has a temperature and pressure, and these are going to be different because the injector is going to be to your temperature.
I think my idea of question was just that I think I'm totally misunderstanding, because my thought process of this question, designing this question, was just that the sludge inside the injector would already have some temperature, and the container itself would have some pressure.
Yeah. So then that could be the case, and then I would ask, what's the point of the injector? Why not just make it a pipe? Why not just have a pipe with a certain temperature and pressure?
Okay. I guess could we do that then? No.
You can, but then you wouldn't have a problem B. You would be solving for
I
a
believe we
return.
can just make it a pump
Okay.
and have the temperature be.
Yeah, and I'm sure the injector is acting as a pump. Like, you could still call it the injector and say the injector is acting as a pump to increase the pressure required for the reaction vessel. Yeah, so this is serving a function. So then the temperature needs to be the same between these two. And then, I don't remember seeing that we were told that the injector was adiabatic. I know that you were asked to say what the assumptions are, but I don't remember reading anything about saying that the system's adiabatic. So probably want to add that in there.
As in, like, if it's adiabatic, we don't have any, like, it's not being, but it actually has some heat, isn't it? Like, the heat of the sludge has to be increased, so it can't be adiabatic.
Say it again?
Like, there has to be, in order for the temperature to increase, well, like, I guess, I wrote adiabatic because I didn't think that increase the temperature in its place where it is right now. But then the temperature, there is like a Q in at the reaction vessel that would cause it to go from the sludge to go from like whatever temperature it was before to the new temperature. But
It depends. It doesn't always have to be a Q. It could be something else that makes a temperature increase or decrease. If you want people not to assume that it's adiabatic, then maybe you can solve for a Q first before you solve for a work term. Or if you do want people to assume that this injector, which is acting as a pump, is adiabatic, then you just need to let people know in the problem beforehand. Because if not, then we wouldn't have known that to make that as part of the assumptions for answer A.
Okay, so put that in the problem statement.
Correct. Yeah. Or you could say like, you could say that it's a perfectly insulated injector that acts as a pump. So if you say it's insulated, then that gives us the hint of we know that means heat is not transferring. You say reaction chamber. I think it's good for consistency of words. Just call this vessel, not chamber. And you say that there's wet biomass, water, and alcohol that drives. That's what's being pumped in around, but what makes the biomass wet is water. So it's like saying you have water and biomass and water and alcohol, so it's a little redundant.
Sorry, did I say that? Sorry, this is writing me. Yeah, you're right.
Well, I think it's just maybe there might be confusion in what it means to call it wet biomass. Wet biomass just means water plus biomass.
Okay.
So it's like you're saying water plus biomass plus water plus alcohol.
Yeah.
And so you can say wet biomass, we usually call this a slurry, so or you can call it a sludge. So this is a biomass slurry or a biomass sludge, which contains the biomass plus water, and then there's also some alcohol in there too.
So I'll just say wet biomass and alcohol.
Correct. Yes. And then what else? Yeah, so, and when you're solving these, your thetas are not at states 1 and 2. It's not in a snapshot within the vessel, it's at the inlet and the exit. So
Okay.
those will be inlets and outlets.
It should be like theta E minus theta I.
Correct. And then, this is an incompressible fluid, so your CP is just C, delta T. I wasn't sure where this P2 minus P1 over theta was from.
So just another short question. On your note of the inlet outlet of the theta,
Mm-hmm.
the enthalpy should also be enthalpy exit minus enthalpy inlet
Correct.
for the W net.
Correct.
Okay. Yeah.
I wasn't sure what this P2 minus P1 over theta term was. And then your work term, you have it as lowercase, which signifies to me that this is intensive.
Sorry, I
But
just
you did
put-
multiply by mass, so that should have been a capital W. Same thing with the one underneath it. Because you have a big capital W total per year is equal to a little w dot, but that should be a big W. And then for part C, you're missing the mass terms associated with entropy that's flowing in and flowing out. So big delta S,
So
your
sorry.
build,
So sorry, I was making notes on that. Could you explain the notation again with the capital letters? You said that should be W, capital W.
yes, it's intensive, but it should be written extensive where mass is because you multiply it by mass molar fluid already. So it's big W. And then for your second law equation, you're missing the entropy associated with mass flowing in and out. So I think it'd be helpful if you wrote out the full entropy equation and then cancel out the terms that you needed to. So your change in entropy is equal to whatever entropy happens from heat crossing the boundary, whatever entropy happens being carried in and out by mass, and your S-gen. So you're solving for S-gen, but you're missing in and out entropy terms. So that means you have to figure out a way to solve for this in and out entropy according to the temperature and pressures from your system. But we don't have tables for this, so that's probably something we might have to provide. You have to like make it up, I guess.
Okay.
And then because so this is an open system, and this is only for not open systems. So